question. This is number 21. We're selling 12 by 12 squares or 13-inch rounds. Which option gives the most rock for the money? So we got 12 by 12 squares, and then we have the 13-inch round one. I kind of did this yesterday. Which one gives me the most stone for the money? If this is you, if you're at, I don't know, Lowe's or somewhere, and you're trying to figure out how to put pavers down, how would you determine which would be the better deal? Jacob? Figure out the volume. Now, in this particular case, it wouldn't even necessarily be volume because they're the same thickness. Wouldn't we really care about area? How much area they cover? Now you can do it with volume because we'll just let the volume be one and then it won't matter. But I think in this particular case, we're talking about how can I cover the most ground? So a 12 by 12 square obviously is going to cover 144 square inches, right? What about a 13-inch round? How am I going to find out how much area it will cover? Jacob? Pi r squared, and the radius would be 6.5. So I don't know what that is. I'll figure that out. So 6.5 squared times pi. And that one is 132.73 square inches. So if you are simply looking to cover the most area, you're going to go with the squares. And practically speaking, that would probably be best anyway because they fit together better. Really, if that's what you're trying to do, is make a path or something. All right, next, what did I pick out here? 22. Free fall of a smoke bomb. So D equals 16t squared. Now, stop and think, what does that equate? They gave me that equation. What does that mean? This is how many feet the thing will fall in t seconds. Real simple concept. All right, so let's see. How long will it take the bomb to fall 180 feet? Well, what would we do? How long will it take it to fall 180 feet? Put in 180 where? For D, sure. So 180 equals 16t squared. T squared equals, I don't know, whatever 180 divided by 16 is. 11.25. And then we'll take the square root. So how long will it take it? About 3.35 seconds to fall 180 feet. All right. If the smoke bomb is in free fall for 12.5 seconds, how high was the airplane when the bomb was dropped? What do you think we'll do there? Anybody besides, I mean, I love Jacob, God bless him, but does anybody, yeah, Jesus?
You replaced the t with 12.5.
Exactly. So we're going to use the same equation. We're just going to put in 12.5 here. And we'll square it and times it by 16. This is not hard, guys. There are a bunch of random different kinds of problems, but none of them are too tough. Oops, 16. Did you get 2,500? So how far up in the air was the plane? 2,500. All right, let's see what else we got. A couple more, then we'll move on to something else. 23. A physics student obtains the following data. Find an algebraic model that fits the data. This is what we did yesterday. When we say find an algebraic model, what we're really talking about is write an equation. What equation describes that? This is the algebraic model for free fall. Okay? We need one for this ball on this inclined plane. Okay, so do you remember what we do? We go to stat, edit, and I can type over or I can clear it out, whatever's easiest for me. Just make sure that if you type over, you don't have any leftovers from yesterday. Oh yeah, make sure you're in the right column. I just put mine in the wrong column. Now, once we get them all in there, kids, you're using your picture to determine what kind of equation, right? So please make sure that your window is set so you're going to get the best picture possible. So maybe our x's should be what? I'm going to my window, and what would be good for my x's? 0 and 10. I probably wouldn't use 0 because isn't that my lowest number? I'd probably go maybe -2. 10 would be okay, but I'm just going to say 7. I'm going to open up my picture as much as I can. And then what about my y's? Maybe -2 to 32 or 35, something like that. Now, if you press graph right now, if you're like me and you press graph right now, nothing's going to happen. Because what do I have to remember to do if I am plotting points? Turn the plot on. Yeah, so yesterday I turned mine off, so I have to go back in and turn my plot back on. And then I can hit graph. Shoot. I had other equations in there. I gotta clear those out. Stat plot is above y equals. So you do second y equals. And then you look carefully at the shape. And right now, we are only doing lines and parabolas. But it will get more complicated than that. But right now, you just look at it, look at all the points that you plotted. And it looks to me like it's a curve, doesn't it? It's a curve. So that's a quadratic regression. So I go back to stat, right, over to calc, down to quadratic regression. And remember, a quadratic is going to come up as ax squared plus bx plus c. And in case you forget that, the calculator tells you. And then it tells you what your a, b, and c are. So it looks like our model is simply 1.2x squared. Is that okay with everybody? You guys have no idea because you've grown up with all this technology, but when I was your age, we were doing these problems without a calculator. And to do that, you have to build a big system of equations and then go through all this. It would take us a period to do a problem that we just did in 30 seconds. What?
Do you feel like you're missing that because you didn't have a calculator? Do you feel like you're missing that and you can calculate problems faster?
We had to. You guys have never really had to. We had to. So probably, although now I'm ancient, so my mind doesn't work as well. Are you here for the learning comments?
Yeah.
Okay, come on in. You're on video, so make it good.
Alright.
Okay, here's about the learning commons. They're going to take just a couple minutes.
Okay, so what what you're getting right now is just like information about the learning commons. And I probably will say a lot that's on there, but just so you can remember. Okay, so the learning commons is new this year. It's in Loretto in room 2210. And it's where you can go to get math help. So any level, you can get help there. And Mr. Leisure runs it along with the tutors. And all the tutors are students, and it's free. You can come at any time. It doesn't have to be resourced. You just have to get a teacher's permission. And so on your iPad, you should have an app called Nexus, which is like an online tutoring app. So if you don't actually want to come to the learning commons, you can do it through there. You will be signed in on there, and we can help you through that. Or if it's on like Mission Monday, you can do that then too. If you log in, if you go on Nexus, if you don't already have an account, just click forgot password. You can create a new one, and then it should work. Other than that, I don't think.
Your username is the first, like, your email without that.
You guys have any questions, you can ask it.
Any questions? Alright, thank you.
All right, you're welcome. Have a great day.
You too.
Okay, so that's an option for you during resource. Whoops, sorry. During resource, if you want to get some help. Okay, so everybody's good on that? So what does it mean when it says find an algebraic model? Find the equation, and if you have a bunch of data points, your calculator will find the equation. Easy. Okay, one more. Let's look at number 47. All right, so Swan Auto Rental charges this for Elaine rented a car for 1 day and she drove 83 miles. How much did she pay? Ramon paid $69.80 to rent a car for 1 day. How far did he drive? So basically, you need to come up with an equation and then use the equation to answer those questions. This is a simple enough problem, you can probably do it in your head, but let's see if we can actually come up with an equation. $32 a day plus 18 cents a mile. What's that equation going to look like? So I heard 32x plus 18 cents, is that right? 18y? Is that right? Okay, you guys aren't probably old enough to rent a car yet, but the amount you pay depends on one thing, right? I mean, once you pick out the car, it depends on one thing, and that is how many miles you drive, right? So I walk in, I'm gonna rent a car. How is my bill going to be calculated? Aren't they gonna take 18 cents times every mile that I drove? And then what else is added into that? The $32. The $32 doesn't have a variable. It's a straight fee. You're gonna pay $32 no matter what. And then you're gonna add on 18 cents for every mile. Does that make sense to you? The 32 isn't going to change unless you keep it for more than 1 day. But this is a daily rate. This is for 1 day. All right, so then it says, Elaine, she rented it and she drove 83 miles. How much did she pay? Well, what are we going to do? We're going to put 83 somewhere. Where's it going to go? It's going to go right here, right? So you're just going to take 32 plus 0.83, or no, 83 times 0.18. So she pays $46.94. Did I type that in right? All right, and then the other guy paid $69.80. How many miles did he drive? What do I do with the $69.80? It goes in here. That's the cost, that's the money. So when you solve that, just like a regular equation, we'll take 6980, subtract 32, and divide it by 18. So it looks like he drove 210 miles. Is that okay with everybody? All right. Now we're just going to do a little bit of random review that's in this section. Solve algebraically. Now, does everybody understand what that means? That means with your pencil and paper. You're solving it by hand. So, what would you suggest if we are solving this big long equation? What would you suggest we do? Combine like terms. And when you say combine like terms, I hope you mean move everything over to one side, because this is a quadratic equation, and we'd like to have it set equal to 0. And then we can pick our method of solution. So I'm going to subtract x squared. I'm going to add 3x, and I'm going to subtract 4. Right, make sure I did that right. I subtracted x squared, added 3x, and subtracted 4. Does that look okay? Now, wide open possibilities. This one, because that number is even, you could even complete the square if you wanted to. You could certainly use the quadratic formula. Anytime you've got a squared equation, you can use the quadratic formula. This one actually factors if you want to factor it. So any of those methods are fine. I'm going to go ahead and factor it because that's the quickest for me. I can't rely on factoring though, can I? Because not everything factors. And sometimes they factor, but they're so complicated it's not worth the energy. Always the quadratic formula, always will work. So what are my answers? My answers are 6 and -2. All right, one more of those, and then we're going to go back to our calculator. What are you going to do with this one? Distribute. And notice when you distribute, it's another x squared equation, quadratic. And what should we probably do with our quadratics? Get them set equal to 0. I don't think this one factors. And I don't really want to complete the square. Why? Why won't completing the square be pleasant? It's doable. Why wouldn't it be pleasant? Because you're going to take half of this and square it, and that means fractions. I don't want to mess with it. So I'm just going to use my quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And I do have a calculator to help me with the arithmetic if I need it. What is that, 50? Is that 105? I don't know, I'm going to wait and have somebody check it for me. Is that okay, 105? Now, does 105 break down? Actually, it doesn't, does it? I mean, it breaks down, but I don't get 2 of anything. So my answer is just right there. All right, now we're going to solve graphically. So let's talk about what you're thinking about doing. You're going to solve this graphically. First thing I'm going to do is turn my plots off. I have an old calculator, and it will not graph with the plots on. I don't know, some of the newer ones might. I don't have a newer one. So I'm going to turn my plots off, so I'm ready to graph it. What are some options we have? What are you thinking about doing? Just moving everything to one side? If we move everything to one side, it doesn't really matter which side we move it to. Okay, so I moved everything over here. You might have subtracted that and moved it over here. Makes no difference either way. If you graph that, what would you be looking for on your graph? By the way, you're going to want to change your window, probably. What would you be looking for? If you set it equal to 0, I don't have any idea what this looks like. I'm making that totally up. You are looking for these points, right? If you have set your equation equal to 0, you are looking for the zeros where it crosses the x-axis. That's perfectly fine. That will work. There's not a thing wrong with it. Did anybody have a different thought? Could we leave it like it is and graph it as two separate equations? And if we did that, we would be looking for where they cross each other, right? So it's about the same amount of work either way. You're going to go into second calc, and you're either going to pick zeros, you're going to pick the intersect. So I don't care. Pick one way or the other and do it, and let's see what answers we come up with. Remember, you have to go in through y equals. You're graphing, so you got to be y equals. I did it with intersect. Did anybody do it finding zeros? Okay, it looks like I only have one point of intersection. Do you only have one zero? Okay, let's make sure we all get the same answer then. And remember, you're looking for an x value. No matter which way you do it, it's the x value that's your answer. I got 2.664543. So, no matter how we do it, we just gotta have a plan. Just gotta have a plan. And then if you're doing intersection, you second calc intersect, or second calc 0 if you set it equal to 0. Yes, Reed?
Does it matter if you put the whole thing?
No, I didn't have any rounding directions, so I wanted to make sure we matched exactly all the way. All right, so that's that one. There's one more. Now, B could easily be done by hand. That one would be a mess by hand. But this one could be done easily by hand. But let's practice one more time with our calculators. So again, either get it all set equal to 0 or graph it as two separate equations. Did you get two answers this time? Those match yours? I rounded those off instead of writing out the whole thing. Okay, so if you were to come in, let's see, do I see you tomorrow? I feel like I never know what I'm doing. I don't see you tomorrow. Of course I don't see you tomorrow. So if you came in the next day, what would that be, Thursday?
Yeah.
If you came in Thursday and I slapped an equation up here and said use your calculator to solve it, do you feel like you could do that using either setting it equal to 0 or using the intersect feature of your calculator? Okay. What do we have to have in order to make that happen? A calculator, right? Okay, here we go. 1.2, here comes the beginning of the main part of the chapter. First of all, what is a function? I've defined continuity up there at the top, and we're going to explain that definition. But what is a function? Start there. A function is what? In your own words. Oh, guys. We can put our iPads down. We don't need our book right now. We really need to be focused totally. And we need to know what a function is. Someone tell me. Tell me anything you know about a function. In math terms. I mean, a function, a mathematical function. Anything you know at all. What?
You plug in something to get an answer.
Okay, so it's basically, it's an input-output machine. You input something and out comes something. And the notation we use for that is generally f of x, but it can be any letter. Our projectile motion formula was s of t, but it was, give me a number, input anything, and out will come an answer. Functions represent ordered pairs. I put in a 3 for x, I get out an 11 for y. That's what they are. They're input-output machines. Now, what is special? If I started inputting, like I put in 3 and got 11, I could put in 2 and get 9. I could generate a whole bunch of points. Zillions of them. What would be special about those points? What makes that a function as opposed to just some random group of points that you might find? What's true of function sets of points? Guys, Hollis and Ludington are freaking out right now. What makes a function a function? Okay. Let me give you a hint. A vertical line test. Remember the vertical line test? Okay. So if you have something, some shape, that passes the vertical line test, it is a function, right? So let's look at a couple, and then you tell me what's going on.
Does that mean like x's can't be the same?
Oh, there it is. Because if you have a shape like this that passes the vertical line test, all of those points have a different x value. But if you have a shape like this, it doesn't pass the vertical line test because this point and this point, this might be 2, 3, and this is 2, -3. They have the same x coordinate. So what is the definition of a function? It is a set of points where no x's or no first coordinates, no x coordinates repeat. Now, if that isn't already in your head, I would suggest you write that down. Because it's a big definition and it's something you absolutely should know. Read. Huh? A function is a set of ordered pairs where the first coordinates don't repeat. No repeating first coordinates. So a function is nothing more than a set of ordered pairs, but you can't have any of the x's repeat. So you can look at a set like this, as an actual set of ordered points, and determine if it's a function. You just look at all these. Or you can look at a picture, right, and test using the vertical line test. There are all kinds of different functions, guys. And there are lots of new vocabulary words that are going to be associated with our study of functions. The first one we're talking about here is continuity. Is a function continuous? In calculus, continuous functions are our favorites. We like continuous functions. Does anybody just want to take a wild guess what it means to be a continuous function? Doesn't stop. Okay, there's a little bit more to it than that. Read. Pardon me?
It goes on forever?
Yeah, that's kind of what they said, and that's a piece of it. We can actually have continuous functions that have limited domains. So, for example, we're going to study 12 very special basic functions, and one of them looks like this. That doesn't really go on forever in both directions. It goes on forever in this direction, but that is a continuous function. This one, which is another one we'll study, is not a continuous function. What's the difference? What makes it continuous? What?
Does it have to touch the origin?
No, it doesn't have to touch the origin. Think about, watch my hand. Watch my hand. When I graphed this one, I put my pen down and I graphed the whole picture. But when I graphed this one, I put my pen down and I graphed this piece, and then I had to pick my pencil up, and then I graphed this piece. If you are continuous, this is not the definition is written there, but basically, can you draw it without lifting your pencil? If you can draw it without lifting your pencil, it's continuous. If it's broken in any way, it's discontinuous. And there are different kinds of breaking that we can have. This picture right here, this one right here, goes with D. It is a non-removable or infinite discontinuity. This is a biggie. These are the strongest discontinuities, when it's actually just broken. Two totally distinct pieces separated by what we call a vertical asymptote. So in your list there where you have different kinds of discontinuities, this is a picture, draw the picture of a non-removable or infinite discontinuity. When you have a vertical asymptote, that is called a vertical asymptote. You have a non-removable discontinuity. By the way, just a little aside, that's the word asymptote. An asymptote is a line that the curve approaches but doesn't intersect. When we pronounce the word asymptote, we do not say the P. It's not an asymptote. It's an asymptote.
So that one's removable discontinuity.
Huh?
That one's removable discontinuity.
No, we haven't done, no, this one's continuous. This one isn't, we haven't done any of the others yet. This one is D. We haven't done A, B, or C yet. While I'm talking about asymptotes, so share a quick story. Used to, of course, have a classroom, have a whole bunch of math t-shirts hanging around on the walls. My favorite one of all time. The administration wouldn't let the kids get this particular shirt. for an athlete that they had them made anyway undercover and gave me one. It's so cute. It's black. And on the front it just says got math, the same as the got milk thing. It's just got math with a big question mark. And then on the back it says, you bet your ass and toes. Isn't that cute? Yes. Anyway, that's one of my favorite shirts. All right, so let's get back to this and figure out, okay, A is continuous, so this is a continuous picture. A parabola is a continuous picture. Draw whatever picture you want as long as you can do it in one fell swoop. So here's a continuous picture. That's continuous. Anything, now make sure it's a function, so don't be doing this. That's not even a function. So make sure it's a function. That one, this one, all those are continuous. Did you draw a circle? I hope not, because does a circle pass the vertical line test? No. Now, what is a removable discontinuity? This is non-removable. There is no way to take this kind of situation out of the problem. A removable discontinuity can look a couple of different ways. It can look like this, for example. So it can be a nice, almost continuous curve with just one little hole in it, somewhere. And the hole wouldn't have to be there. The hole could be up here, anywhere. But that's called a removable discontinuity, and you're going to understand that as we get farther into the chapter. But it can look like that. It's discontinuous because when you draw it, you have to like skip over that point. But it's not as serious as this. Jacob?
So with a removable discontinuity, you don't have to start at that dot, you just have to jump over.
Yes, right. That dot can be anywhere on the curve. Now the other situation you can have is, you can have kind of the same picture. You can actually have the dot that was there could get moved somewhere else. So this is also considered a removable discontinuity. So here, that dot is just totally missing. Here, that dot is placed somewhere else, either above or below the opening. Now, is this still a function? Yes, because even though it looks like it hits twice, it really only hits here because that dot is open. You couldn't put that dot over here because then it would not be a function. So if you're going to have that random dot, it has to be above or below the hole. Does that make sense to you? All right, and then we have what's called a jump discontinuity. These are my personal least favorites. And a jump continuity, the most famous one, is one you've seen before, I think. Have you seen things like that? Maybe you call them step functions. Maybe you call them that's a greatest integer function. But that's an example of a jump discontinuity, where you have a piece of curve, and then you jump to another piece, and then you jump to another piece, and so on, and so on, and so on. That's called a jump discontinuity. Those functions are generally written, there's no, these guys you can simplify and rewrite. These guys, there's really no simplification. They just come out. When you write the equation, that's what they come out looking like. They may be my least favorite, but they're probably one of the most applicable, because the classic example is when you go down to the post office, you're going to mail a letter. If it weighs half an ounce, you pay 50 cents. If it weighs 3/4 of an ounce, you pay 50 cents. If it weighs up to an ounce, you pay 50 cents. But what happens if it weighs more than an ounce? 50 cents becomes $1. You need 2 stamps then. And then up to 2 ounces, you can get by with 2 stamps. And then what happens if you got that next part of an ounce? It jumps to 3 stamps. That's an example of a real life application of a step function. Okay, so we have continuous functions. We drew one. We have removable discontinuities that have a hole in the picture and then either a random dot somewhere or not. We have our jump discontinuities that are like jumping all over the place, usually predictably, but sometimes random. And then we have the non-removable discontinuities, which are the actual asymptotes. So last year, another example of an asymptote picture. Did you guys graph any trig last year? Any trigonometry? If you graph you know that sine, cosine, and tangent. If you graph a tangent curve, it looks like this. See how it's broken by vertical asymptotes? Those are non-removable discontinuities. Vertical asymptotes. Okay. That definition of continuity, I want to talk about that. I'm going to use the picture that I had where I had an opening here and a dot here. The definition says that it's continuous at A, and I'm going to let that be A, whatever that number is, 2 or 5 or 3.5, whatever. I'm going to let that be A. The limit as x approaches A of your function is the same as you get when you plug in A to the function. Now that is serious math notation. It's easy. Let's talk about it. Make sure you're not scared by it. The limit as x approaches A. So what I want you to do is take your 2 fingers and we're going to approach, this is A, what I've called A, and I'm just going to bring the curve in. And what is happening to my fingers? As I get, here's A, this is A right here. As I get closer to my A value, if I come in this way, get closer to my A value, what are my fingers doing? They're coming together, aren't they? If your fingers come together, you have a limit. So it's all good. Now, the definition says that where your fingers come together have to be where the solid dot is. So if you're going to be continuous, your fingers have to come together at the dot. Well, look, do my fingers come together at the dot? Here's the dot. Here's where my fingers are coming together. Are they coming together at the dot? No. What would happen if I move the dot down there? Now, are my fingers coming together at the dot? And what does that do to my picture? Makes it continuous. That's the definition of continuity. As you come in on both sides toward the point in question, A, your fingers must come together, and they must come together at the function value, which is the dot, the location of the dot. So if I look at just one of these branches, let's suppose I want to know if I'm continuous. This is A right here. Is it continuous at that point? Yes, because my fingers are coming together at the dot. Okay, now when you're in your calculus class and your professor asks you to define continuity, please don't say, it's if my fingers come together at the dot. That's not the mathematical definition. This is the mathematical definition. But it means your fingers are coming together at the dot. All right, so now we're going to consider function, and we are going to answer a ton of questions about it. This is called, question 2 is called function analysis. You are going to analyze this function. Now, I picked that one because it is a shape I think that you're familiar with from last year. Does anybody remember? You know an x squared is a parabola. What is an absolute value? Does anybody remember the shape of an absolute value, Ellen? It's a V. And this V, because of the numbers in it, this V has been moved. The normal one is at the origin. But these numbers move it. Does anybody remember? I know you talked about this last year. Does anybody remember how this moves? Grace?
Left 2 and down 1.
It is. Very good. Left 2 and down 1. So we just got our standard old V, and I'm not worried about you plotting points. The only point that's important is this one right here. Left 2, down 1. We're going to talk more about that. Hopefully you remember it, but we will spend some time on that. A lot of time, actually. So this is my curve. All right, that's my shape. Number 1, is it a function? Yes. Does it pass the vertical line test? Yes. So it is a function. A, is it continuous? Can I draw it without lifting my pencil? I absolutely can. There are no breaks in it, so it is continuous. B, is it increasing or decreasing? Now that's a new vocabulary word, but you know what those words mean. What does increasing mean? Going up. What does decreasing mean? Going down. So would you classify this function as increasing or decreasing? It's actually a little of both, isn't it? The determination for increasing and decreasing is what happens left to right. Chase, you paying attention, sweet pea? All right, action's up here. Left to right. So as I draw left to right, what's happening to my pencil right here? It's decreasing, right? And then what's happening to my pencil here? Increasing. So what we'll write is, we are decreasing from negative infinity to 0. These are x values. We are moving left to right. That is an x motion. So as I move left to right, not to 0, decreasing to negative 2. Sorry, I thought it was at the origin. I'm decreasing until I get to negative 2. And then I am increasing from negative 2 to infinity. Again, I'm looking left to right, so x's are the important numbers. X's are what I'm looking at, left to right. Right? Because I'm looking at the x values. I'm moving left to right, so I'm answering a question about x's. You use x's in the interval, not y's. Left and right's which variable? X. So if I'm talking about motion from left to right, I'm using an x. Now, notice that I used parentheses. I know part of that makes sense. We always use parentheses with the infinities, right? Anybody want to explain why I used a parentheses here and not a bracket? What is happening at this point? Is my pencil going up or down at this point? Neither one, is it? It's not going up or down at that point. It goes down until it gets there. It goes up after it gets there. But at that point, it's neither increasing nor decreasing. So that point is not included. It will never be included if you have a change in direction there. Okay? Alright, so that takes care of increasing, decreasing. Bounded, above, below, or bounded. Any idea what that means? Where it comes together. Actually, it is where it comes together in this case. Bounded means, bounded below means it has a floor. Bounded above means it has a ceiling. And bounded, or just the word bounded, means it has both. Now, does this picture have a floor? In other words, is there a point beyond which it does not go down anymore? Isn't this the floor? It doesn't get any lower than that, does it? Now, when I'm talking about bounded, Reed and everybody else, bounded is ceiling and floor. That's a vertical thing. So what am I looking at in terms of variables if I'm talking about bounded? Was, because bounded is vertical. So this one is bounded below at y equals -1. In other words, its floor is at -1. Does this have a ceiling? No. So it is not bounded above. You don't have to write that down. But that means it's not bounded, because to be bounded, you have to have a floor and a ceiling. So this one is just bounded below.
What was the example you were doing, like, if there was, like, a ceiling?
It would be what?
There's, like, ceiling.
That would be like a sine curve,
Okay.
right? And we're going to study all of these weird shapes. But for now, we're going to have to stop, even though we would like to keep going. Hey.
I have another question for you.
Yep, let me turn this off real quick.